have a couple brief announcements tonight before we have tonight's speaker's presentation. First of all, I announce that the next meeting of the Catalyst Club will be in Ashland on March 15th. Dr. Carl Mueller from Penn State University will be speaking. His topic that evening is scheduled to be high-resolution solid-state NMR experiments. At this time, I'd like to ask Barbara Warren to make an announcement about the Spring Symposium.
Tri-State Catalyst Club Spring Symposium. For anyone who did not receive an announcement, just tell me after the meeting and I'll be happy to give you one. It is April 12th to 13th, and our plenary lecture will be Gary Howler. We're also going to have several other distinguished speakers from our club. It looks like a very good meeting. It'll be a two-day meeting, mainly heterogeneous, but also we're trying to emphasize the homogeneous catalysis aspect this time. So anyone, we encourage you still, you may submit an abstract. We have a few slots. We're particularly encouraging homogeneous catalysis. Any of you who would like forms to register, please see me after this talk. Charleston.
Another schedule item, I'll just put a reminder in that the national meeting out at Snowbird, Utah's deadlines are rapidly approaching on that, so if you might keep that in mind for your summer plans. I don't know of any other business of the club this evening, so unless anybody else has any announcements that I'm not aware of, we'll proceed on to introducing tonight's speaker. Tonight we are fortunate to have a talk from one of our own club members. He has been long active in the club, having been our past director, president-elect, and most recently president. Fred Tungstate, tonight's speaker, started his profession in chemistry with earning his bachelor's degree from Indiana University, then proceeded to earn a PhD in chemistry from the University of Tennessee. He has been employed in a number of positions with UCI, and just this year starts on a new position in the sales area. Previously, from 1986 through last year, he was manager of research and development for United Catalyst Incorporated. Previously, he was manager for research and development at Zeochem, which is partially owned by UCI. And previous to that, he was a group leader in research and development at United Catalyst. He's also been active outside the club and outside of work in the profession of chemistry. He's been a part-time lecturer for several short courses. He's also been a part-time lecturer at the University of Louisville. Most recently, in terms of recognition, Fred has been awarded the Kentucky Academy of Sciences Outstanding Industrial Scientist Award. Tonight, Fred is going to speak to us on a talk entitled EBFU-1, which is, I interpret to be a catalyst name, a new zeolite-based benzene ethylene alkylation catalyst. Fred?
Thank you, Dick. I'd like to start tonight by thanking all of my co-workers and superiors at United Catalyst whom have supported all of our activities in the Catalyst Club for many years. Mr. Alsmiller, Bob Alsmiller, many of you know, who is the Vice President of Sales in hydrogenation and refining of zeolite catalyst. We're fortunate to have him here tonight. Thank you, Bob. Mr. George Bueller, who is Vice President of Sales of fats and fatty chemicals. And of course, Mr. Carl Russ, who's Vice President of our technical division. So a lot of our work and support has been supplied by those gentlemen at UCI, and we're very grateful. Well, I've been active in this club for many, many years, and due to the nature of our business, it's rare that we could give presentations. It's even almost as rare that we could even ask questions and discuss the presentations of other speakers. But fortunately tonight, I've been allowed to give a presentation on a new catalyst area that we're entering into, and it relates to the alkylation of benzene with ethylene over zeolite catalyst. Our catalyst is called eBuff-1, and it is a zeolite-based alkylation catalyst. The eBuff, since you probably can't figure it out, I'll explain the acronym to you. EB stands for ethylbenzene, U stands for United Catalyst, and F stands for FENA, and it's version number 1. And this paper has the co-authors of Dr. James Butler of FENA Research and Technical at Deer Park, Texas, Dr. Mark Kuchenmeister, also of FENA Research and Technology, Deer Park, Texas, and Bob Alsmiller. Let me go into a little background, if you will. In November of 1994, United Catalyst announced in a styrene symposium held here in Louisville that we had developed a new benzene alkylation catalyst. This came about through a cooperation with FENA Research and Technology. But it all goes back to 1980 or so. United Catalyst got into the zeolite area by forming a joint venture with a Swiss company called Chemie Unicon, and that company is called Zeochem. And they decided to build a plant to manufacture zeolites in the United States. And the primary products of that plant are the A's and the X-type zeolites, which are desiccants and separations media. At that time, we also began an effort in research into the catalytic grades of zeolites. In the mid-'80s, our parent company, Sud Chemie, also became interested in catalytic grade zeolites and instituted a research and development program of their own, and that resulted in the commission of a large-scale zeolite manufacturing facility in Richards Bay, Republic of South Africa. That is our source of our catalytic grade zeolites, and that plant is a very large plant. It makes it has a very large annual capacity. It makes all catalytic zeolites of commercial interest. And for those of you interested in the field, that is the Y zeolites, that is Mordenites, it is Beta, and in addition, and in particularly, it is the Pentacyl type zeolites, which are the so-called ZSM5 zeolites. We became interested in this area, but as many of you know, for many catalysts of this type, there's a barrier to entry into this market. And that barrier is you have to have access to an operating facility. In other words, you can develop a great catalyst and you can do all the lab work on it, but you still have to get that catalyst installed in a commercial operating facility and prove it. This is where the cooperation with FENA came in, because FENA is a 50% owner in the world's largest ethylbenzene styrene monomer plant. They have a facility at Carville, Louisiana. The company is called Cosmar, and it is a 50-50 joint venture of FENA oil and chemical company, and General Electric. And they alkylate benzene with ethylene to make ethylbenzene, which they then dehydrogenate to make styrene monomer. And this styrene monomer is then sold and given over to a polystyrene manufacturing facility. A large portion of that polystyrene goes into a plastic that General Electric makes called Norel plastics. And it's a blend of polystyrene and polyphenylene oxide. So we were able to gain a cooperative agreement with FINA, and therefore we were able to develop a catalyst and get it installed in a commercial facility and prove the worth of that catalyst. When one goes about developing a catalyst of this type, there are many requirements, and one of the known requirements of this catalyst is that it be acidic. The old technology, I say old technology, but in reality, it's not old technology. This technology still makes 2/3 of the world's ethylbenzene, and that is the aluminum chloride liquid phase alkylation technology, is a known acidic catalyst. However, there are many problems associated with using that aluminum chloride technology. It is difficult to manufacture, it's difficult to ship, it's difficult to load. Not the least withstanding of, it is extremely corrosive. In a few years, your catalyst plant ends up in your product, or your operating facility ends up in your product. But the zeolite technology was developed to overcome some of the limitations of this aluminum chloride technology. Well, in addition to being able to alkylate the catalyst, in order to make a catalyst work in a mobile badger plant, a catalyst has to be able to transalkylate also. And so therefore that puts some specific acidity requirements on it. Basically, the acidities required for various chemical reactions are summarized here. The highest acidity is for cracking, and it's approximately equal to that for alkylation, going all the way down to the lowest acidity required for cis-trans isomerization. Perhaps this might be a little more representative. It gives some relative degrees of acidity. And you can see that the cracking and alkylation acidity are quite a bit larger than most of the other types of activity. Well, transalkylation is a process that involves a cracking reaction. And so therefore, the first thing that you have to design into your catalyst is bifunctional acidity. It has to have the acidity required for alkylation, and it also has to have some cracking acidity, which we can translate as transalkylation activity. For that reason, we chose to make our catalyst out of a known zeolite, strongly acidic zeolite, which is the penicil zeolite, ZSM5. Because of its pore size, many zeolites are acidic, but the intermediate pore size of the ZSM5 is ideally suited to reactions of small aromatic compounds. So you can get shape selectivity with ZSM5, which will tend to limit the multiple alkylation. It doesn't stop it, but it tends to limit it. So we decided to make our catalyst out of ZSM5. In addition to alkylating, there are a number of secondary reactions that this catalyst has to perform. all of the higher alkylated species like diethylbenzene can be transalkylated with benzene to make two ethylbenzenes, which is the primary product of the reaction. So you can take a byproduct with one excess of one of the reactants and make more product. These other products, the way they operate these reactors is that pipeline benzene and pipeline ethylene are put into the top of a quench type reactor. Now, for those of you who don't know what a quench type reactor is, it is a single reactor with multiple beds, but it has the feature that you can add additional reactants in between the beds. This reaction is highly exothermic, so one of the ways that you can control the reaction, other than going to a tubular reactor, is to quench the temperature by adding more reactant in between, a colder phase reactant in between the beds. So you quench the temperature, you add more reactants, and you make more product. Well, unfortunately, when you add the reactants, primarily the ethylene, will oligomerize thermally before it can ever approach the catalyst when it's injected into the hot zone. The ethylene oligomerizes to various types of products, but then the acidity of the zeolite will crack it back to various olefins, propylene, butene, ethylene, in fact, which you're not worried about because that'll just alkylate again and make your primary product. But you will get byproducts of cumene, which is propylbenzene, and you'll get butylbenzene, and you get a whole list of byproducts, which I'll show you later on. But the catalyst has to be able to alkylate or transalkylate all of those. Well, these secondary reactions are favored at higher temperature. The dealkylation reaction is favored at lower pressure. And the transalkylation reaction is favored by a longer residence time. So you have a large number of conflicting requirements, and the operation of one of these quench reactors is not an easy operation. It's a nightmare to run, as a matter of fact, and they're continually adjusting quenches, temperatures, pressures, and all things like that. However, the catalyst does a very good job, and one of the other design problems that we had to encounter at this facility is they required a very special catalyst shape. And the reason is they couldn't stand a large pressure drop. In a few moments you'll understand why, but we, United Catalyst, drew on its forming expertise to come up with a catalyst shape for this catalyst, which all at the same time give a larger surface area because it's a diffusion controlled reaction and most of the reaction occurs on the surface. So we increase the activity and decrease the pressure drop all at the same time. UCI calls this shape the CDS shape. And basically, CDS stands for computer design shape. And here I've shown, you have the standard, say 1/16 inch cylindrical or round extrudate. MSci and various other peoples have come up with various other shapes. Probably the first one was the trilobe, which is just a 3-lobed extrudate. And then came the quadrilobe, which is a 4-lobed extrudate. And we came up with the CDS shape. The problem is with all of these materials, if you can just think, this lobe could nestle right into that slot there, and these things could dense pack and nestle together. and actually cause large pressure drop because you don't have a void space there. So United Catalyst came up with a shape which gives an imposed void space in the reactor. We designed a shape whereby there was void spaces, the opening of which was too small for the lobes to enter. And so you could not nestle these particles together, and you have an imposed void space. And we called the shape the CDS. Now, the details on the CDS shape are as follows. You get a relative surface area, geometric, we call it geometric surface area, external surface area, on a CDS that is over 1.5 times as much as on a regular extrudate. And so if you have a surface diffusion control reaction or surface reaction, that's highly beneficial. At the same time, you get 90% of the pressure drop. So you have several ways you can go. You can make this in an equivalent size and get the benefit of the increased geometric surface or increased activity, or you can make it slightly smaller and get the benefit of the same pressure drop but much higher activity. So we generally make it just a tiny bit smaller than the regular. For the 1/8 inch extrudate, we'll make a 1/10 inch extrudate, a CDS extrudate. And this also has the effect of making up for the lost amount of material due to the lower density. So we can get almost as much in the reactor at this slightly smaller size with the benefits of higher geometric surface and lower pressure drop all at the same time. The equivalent materials in the 16th, we would make a 1/20th inch CDS. So it sounds too good to be true, but it works. Now, just to show you that it does indeed work, we ran some pressure drop tests. We've got pressure drops on just a blank tube with ceramic support material in it, in which we assigned a 0 delta P. And the regular 1/8 inch smooth extrudate, we saw a 40-pound pressure drop at these flow rates, whereas with the 1/10 inch CDS, that pressure drop was cut in half. 20 pounds pressure drop. So we had a good active acidic catalyst, and now you're going to get to learn why we had to do all of this. Because these are the process conditions at Cosmos. These people run space velocities that you wouldn't believe down there. They run two 4-bed interstage quench type reactors. And they run at a gaseous hourly space velocity of, I've got a better slide here. They can run those reactors either swing, which means that one is on and one is off, or they can run them parallel, which means that they split the flow and goes through the reactors. If they run them in parallel flow, they're running 7,000 to 8,000 gaseous hourly space velocity. And for those of you whom that's a foreign number to, a good typical number would be like 4,000, let's say. So, but then they have to regenerate the catalyst. Okay, the deactivation mechanism is coking because of all of this cracking and transalkylation that's going on. The catalyst cokes, and so when they swing one reactor offline to regenerate it, they don't necessarily slow that plant down. The other reactor takes the full load, and now they go up to 12, 14,000 gaseous phase velocity. They've only got 550 cubic feet of catalyst in each reactor, and so they have this tremendously large flow rate. I mean, it is huge. You can't believe it. So they have to have a catalyst that is both extremely active and has a low pressure drop. They go in to the top of the beds about 740 or 750 Fahrenheit, and they take a delta T of up to say 820, 830 Fahrenheit. So we're talking about 80 degrees Fahrenheit delta T through these beds. And then they come out and quench with additional benzene ethylene and drop the temperature back down to 740, and then they go into the next bed. The pressure is 280 to 400 pounds per square inch gauge, and there's the delta P's across the catalyst bed. In parallel flow, they run 25 to 30 pounds pressure drop across these beds, and in single flow, they'll run 60 to 80 pounds, because they're essentially putting the whole plant through one reactor while the other is offline to be generated. Benzene to ethylene molar ratio is on the order of 7 to 12, and even at that, even with the high benzene in there, you still get this ethylene oligomerization, which contributes to the byproducts. Well, we installed this catalyst at Cosmar in March of 1994, and they were generous enough to keep track of the data for us. And this is a summary of the data that was the operating results over a couple of month period. They really try to operate at 100% ethylene conversion, and that number probably should be 100% ethylene conversion, because they have no facility for ethylene recycle. The excess benzene comes out in the first distillation column and gets recycled back around to the reactor. But any ethylene that breaks through is separated out as light gases and goes to flare. And so that's just an operating loss that they just don't want to bear. So they run this plant to try to run it at 100% ethylene conversion. They run about 227 gallons per minute of PET recycle. The distillation train is set up to take benzene off in the first column, which is recycled. It's set up to take ethyl benzene product off the second column. And then the third column is the multiply alkylated species that they can distill and get off and recycle back around into the reactor to be transalkylated. And then the still bottoms of that column are the heavies, which they can't do anything with. Well, there's a lot of information in this chart. I kind of sneaked it by our FEMA friends because it looked like to be a simple little chart, but if you do some math on this, you can figure out from the PEV residue ratio to EB and the PEVR out, you can figure out how much material this plant is making in a day's time. If you do the math, it'll be over 6 million pounds a day of ethyl benzene. And that'll give you some idea of the quantities of materials they make. They make substantially above 2 billion pounds per year of styrene monomer in this facility. And so that's a number I have trouble imagining how much that is. The ethylene to EB ratio, theoretical there is 0.2642. And so this catalyst is fairly selective. I mean, it's fairly close to the catalyst ratio. So I managed to sneak in the capacity of this plant and the selectivity and a lot of other things in this slide. Now let me show you the nightmare that they have. This is a reactor effluent analysis. There's everything in the world in that reactor effluent. Primarily, they've got such a high benzene to ethylene ratio that most of their effluent is unreacted benzene. And their product, ethyl benzene, runs 18–20% of the stream. But look at all of these byproduct impurities. Perhaps the most byproduct impurities are the diethyl benzenes, which are the doubly alkylated. And you have ortho, meta, and para diethyl benzenes, which have to be recycled back around. But you also get cumene in a relatively large proportion. In propylbenzene, you get a relatively large amount. That is the real problem in operating these plants, because those things can be separated out of the product. There is, however, components of that stream which are extremely difficult to separate out, and those turn out to be the xylenes. The ortho, meta, and para-xylenes. Just look up in Chem Rubber Handbook sometime the boiling points of ethylbenzene and ortho, meta, para-xylenes, and you'll see immediately why those are very difficult to separate. Well, as a matter of fact, they don't do a very good job of it at all. And those xylenes are carried through with the ethylbenzene product. They go through the dehydrogenation reactor, and they end up as impurities in the styrene monomer. And so that's a big deal with these people, is trying to get the impurities in the styrene monomer down, which are primarily the ortho, meta, and para-xylenes. Interestingly enough, the dehydrocatalyst, which is an iron-based catalyst, many of you may be familiar with ours, which is the iron-based ethylbenzene dehydrogenation catalyst that makes styrene monomer, selectively destroys orthoxylenes, but not meta and para. And so I have no explanation for that. I haven't thought about it very long, but you still end up with 1,500, 2,000 parts per million impurities of xylenes in the styrene monomer. And this is a problem for them. Well, let me show you what they're able to separate out in the third column. This is it's called the recycle, PEB recycle. This is what goes back over the catalyst and has to be transalkylated in some fashion. You can see that it's primary, the diethyl benzenes are an extremely large amount, 42–43%. The next largest is n-propylbenzene, and then you have cumene. It has to go back over the catalyst, and the catalyst has to crack the alkyl groups off of these, and then that benzene that's left is either alkylated with duethylene or with some olefin formed in this cracking transalkylation reaction. But the important thing is that what goes into that reactor is not pure reactants. It's not just pipeline benzene and pipeline ethylene. It is those things plus all of this material here. So that catalyst has a huge load to bear, and it must be a well-designed catalyst to be able to both alkylate and transalkylate at these extremely high rates. And just for completeness, these are some of the things that you can't do anything about. They're the still bottoms in that last column, and they have to be sold as fuel value or solvents or whatever you can do with them. But they make a little bit of everything in there. They make multiple ring compounds, diphenylmethanes, and then they've got a category called heavies. Well, when I asked them what heavies were, it turns out that their definition of heavies is what they couldn't identify in the GC. So it was anything that they couldn't identify in the GC was so big they couldn't identify it, is just called heavies. Let me show you a few charts of the operating performance of this plant. This is just a 2-month period of time where the plant was operating at 90-95% rates. Now, there's something interesting about this. When I would go to visit Cosmar, they'd be running X gallons of benzene a minute and X amount of ethylene, and that would be 90% rates. I might go back to 2 weeks and they'd be running X minus 200, and that would be 94% rates. And so I'm not sure that I understand exactly what these rate numbers means. All this means is that our catalyst was loaded into the plant and ran extremely consistently over a 60-day period of time, except for an upset there when they blew a gasket on the reactor. I have an interesting story to tell you about that sometime too, if you ever want to listen. But, one of the key parameters, and this is a purity question, and this is one of the things that the plants follow extremely closely, is the xylenes in the EB relative to the rate that they're making. And here we are lined out and operating at about a 1,700 parts per million xylene rate in the ethyl benzene. Over this long period of time, the upset gave us a problem. The xylenes went through the roof. If you remember, the xylenes are favored at higher temperature, and so they probably had some sort of an excursion there where they lost control of the temperature, and hence the xylene shot up. But they were able to get it back under control and get the plant to operating again. This is, comparatively speaking, we've been told, is a good number compared to the existing other catalyst supplier. The other people guarantee less than 2,100 parts per million xylene in their EB, and so we think we've got a good catalyst. As I said, you have to recycle these materials back through the reactor and transalkylate them. And one measure of how well your catalyst is transalkylating is how much are you recycling around. And it turns out, as the catalyst ages and coats, you generally tend to make a little bit more PEB that you have to recycle back around. So it's a snowballing effect, but just after regeneration you start out low and the PEB recycle rate gradually rises over a period of time. Now what happens is these plants have no storage facilities for this PEB recycle. Whatever comes out the bottom of the reactor in a very short time goes right back in the top to be transalkylated. It doesn't go in a tank to be held, so this plant, in order to keep it operating, must transalkylate. And once that recycle level rises to a certain level, they can no longer operate. Their distillation column goes down and they have to stop and regenerate. So it's very important that your catalyst be able to transalkylate well. I have another slide here just to show you what happens over a period of time, you get down near the end of the cycle. PEB recycle rate goes way up, and the residue rate goes way up, which is the byproduct that you can't transalkylate. But then you regenerate, and you come back online, and now you have very high transalkylation capability, so you can work off the high levels that you built up. And you can work it off very rapidly back down to a reasonable level from which you start building up again until you can no longer run and you have to regenerate again. So that's their means of determining when is it time to regenerate and when is the catalyst coked. Well, it also turns out that in these reactors, even a heavily coked catalyst has a multitude of alkylation activity. So it'll keep on alkylating long after it's heavily coked, but it won't transalkylate. The coke is a deactivation mechanism for transalkylation, and so you must transalkylate, or you must regenerate to regain your transalkylation capability. Were it not for that, these catalysts might run quite long periods of time without regeneration. And one way to look at that is, well, why should you put this stuff back in the top of the reactor? Well, that's the way the reactors were designed. One of the things that we're going to look at in our future work is to come up with catalysts which transalkylate longer, do not deactivate as fast, or do not coke as fast, so you're able to keep them online longer between regenerations. And anyone who's worked with zeolites knows that the primary way that you kill zeolite catalysts is to regenerate them. They seem to have only so many regeneration cycles in them, because in this case they're doing a coke burn. And so they're seeing elevated temperatures, they're seeing high partial pressures of water, they're seeing carbon dioxide, carbon monoxide, all of the things that are generally detrimental to zeolites, they're doing when you regenerate. So they have only so many regen cycles in them, and if you use those up, then soon you can't regenerate anymore. And in fact, a dead catalyst is defined as one which will not transalkylate anymore. But it's still got a world of alkylation activity left in it. Speaking of regeneration, just to show you, when we first put this catalyst in at Cosmar, there were, of course, a couple of overriding risks. One is that the plant would crash and burn, and the people wouldn't make ethyl benzene. After we got through that phase, then we got to the phase, well, can you regenerate it? And so we in fact did regenerate it. There was a scheduled shutdown period after 30 days in the qualification trial of the catalyst, where it was shut down, regenerated, and brought back online just to prove that it would regenerate, and it was going to last more than one cycle. And here's some data on the really important aspect, which is, will it transalkylate again after you regenerated it? And the polyethylbenzenes are the EB ratio is an indicator of that, of how much you make. And you can see that on the initial run, that the regenerated activity is a perfect layover for the initial activity. So we came out of the first regeneration with absolutely no damage to the catalyst. I don't know what that is. It's a plant upset in some way. But by now, they have regenerated at least 4 times, I think. And the catalyst has been on almost a year and is performing just as well as it did the day that it was loaded. I have some other slides here, but I think I'll stop at that point and just acknowledge some of the peoples who were also instrumental in the development and installation of this catalyst. There were some people at Cosmar, Marcus Ledoux, good old Cajun, as the engineering manager. Louis Lawrence is a process engineer. There's a gentleman at Phoenix Oil and Chemical Company called Dr. Jim Merrill, who did pressure drop test, activity test, and that sort of thing. And then at United Catalyst, Bob Rowley in the pilot plant worked quite a long time in making differing compositions and differing shapes and all of that sort of thing in the catalyst. And Troy Wise is a gentleman who oversaw the first commercial production of this catalyst in our manufacturing plant at the West plant. So I'd like to thank those people, and I will go back and I can't stand it. I'll just have to dig this slide out and show it to you. I know you're dying to find out what the catalyst composition is, and you're not going to do that. But I will give you some information about it if I can find it.
Mostly silica?
Yeah, it's highly siliceous. Yes, it is a highly siliceous material. I'll give you a little bit here. This is what you can't carry around with you. And it's a 10th-inch extrudate. The bulk density is about 27 pounds a cubic foot. It's a fairly weak catalyst, but believe me, that works. It has quite high pore volume, which, and it has a reasonable surface area, and it's pentosyl based. It's ZSM5 based. It's a modified ZSM5. It's a composition of the catalyst. So with that, I'd be glad to entertain questions.
Is the regeneration done in situ?
Yes, it is. It's a coke burn with air, slowly bleeding in air, and just burning with the coke.
You have to control the temperature so that it
Yes, indeed. You control just the way you would regenerating any other catalyst like that, and you see an exotherm and you cut the air back, and when it cools down, then you give it a little more air and burn off some more. And you can see the temperature go down through the beds. So.
The shape you have,
Yes.
did you consider other shapes, like holes in the middle of it? Is there a reason you didn't do that?
Yes, indeed.
What?
If you calculate the geometric surface area of those shapes, they are not as high as the CDS shape. In addition, there are some manufacturing constraints in the die manufacture which require that hole to be a certain size, and you need a certain wall thickness. What that translates out in layman's term is that particle becomes very low density. In other words, you have a very low mass in a unit volume, and these reactors are a certain size, and in the end, mass is what determines your product make and your life and all of that. And so there are a number of reasons why the hollow extrudate, if you will, was not the one of choice. It does have low pressure doubling. Yes, Ms. Peck.
Brett, at those conditions, I think is your benzene liquid phase at those conditions, and your ethylene is
No. They vaporize the benzene.
so it's just a gas phase reaction.
It is a 100% gas phase reaction. Well,
And the
wait a minute, I'll qualify that. I'm not so sure that some of this heavy crap that you circulate back around is not liquid phase on the catalyst surface. I'm not so sure of that. But the reaction of benzene with ethylene is gaseous phase.
And your cumene
Yes,
is, I mean, your styrene
yes,
is in the gas phase.
yes it is.
So some of your heavies.
Well, we make EB out the end of this reactor. Now, they go into another reactor, which is the dehydrogenation reactor, to make the styrene monomer. But those are also gas phase reactions. So I wouldn't bet that some of this stuff isn't so heavy that it could be condensed phase on the catalyst surface, leading to a coking mechanism.
But it's not going to come off under your reaction conditions. It's really just going to stay on the surface.
Yeah, it's kind of just going to lay there and do something. Unless it gets cracked, see, you can get some light ends, and you can get some benzene, which will then re-vaporize. If it doesn't get cracked, if it gets realkylated and gets heavier, then you're dead, kind of. It's kind of just going to lay there, and that's why you coke up over a period of time. Yes, ma'am.
You said a substantial proportion of the alkylation technology is the old Friedel-Crafts
Yes.
technology. In
2/3.
the U.S., how does that break down in the U.S.? And what size plant is this compared to other plants in the U.S.?
This
For
is
Applebee's.
the largest,
In the
the
U.S.?
world's largest EB styrene monomer plant. Others run anywhere from 600,000 pounds per year to 1.8 billion pounds per year, in that range.
And Friedel-Crafts is done in the U.S. as well? A large
Yes, it is.
proportion of it is?
ARCO practices Friedel-Crafts at Channelview, and they also practice zeolite technology. They have 2 units, one of which runs the old aluminum chloride and one of which runs the mobile bedroom. And so I would guess, there's only 6.
I'd say it's about half and half in the United States in terms of plants that run the new zeolite technology, because the newer plants that are being built in the Pacific Rim area and things like that are all going with the mobile badger technology. But because the United States has been in styrene production a little bit longer than other parts of the world, they still have that old aluminum chloride technology still around. But the revamps and the newer plants that all been built, like Sheldon, Canada, and like Chevron and Pascagoula, and like Westlake, they're all the newer technology. Sterling is old technology. South America's old technology.
And as a matter of fact, Cosmar was started up as an aluminum chloride plant. In about 1980 or 1981, they revamped and switched over to mobile badger zeolite technology. And so they were originally an aluminum chloride Friedel-Crafts plant. Yes, ma'am.
You said the catalyst has a finite lifetime number of regeneration cycles. Is this like a batch unit, or is there any capability to add makeup catalyst?
No, this is fixed bed. You have to open it up and unload it and reload it just like a HDS reactor or
Is there
something like that.
any plans in the future to make it more continuous?
Actually, if you were a chemical engineer faced with the conditions that they're faced with to operate these plants, the ideal design for a diffusion-controlled reaction with severe heat transfer problems is fluid bed reactor. I know of no one who is investigating that right now. So, I mean, what they're doing is Mobil just came out with what they call their 3rd generation technology. And that is to decouple the transalkylation from the alkylation. And they build a 3rd vessel, and instead of recycling these PEBs back through the regular reactors, they do a liquid phase transalkylation in the 3rd vessel. And all they have to add there is excess benzene and the appropriate catalyst. So one of our goals is to, we think that we can design a catalyst that will transalkylate better and last longer in existing technology plants. we also think that we can design catalysts which will minimize the xylene make. One of the impetus, the main impetus for the third generation mobile technology is its claim to reduce the xylenes in the styrene monomer down to 1,000 parts per million, which is, say, almost a 50% reduction. And so that's chiefly the, people want pure and pure feeds for their polymerization reactions, and these people are no exceptions. That's it.
Back in the early days of ZSM5, it was always marvelous that you could never make these catalysts coke. And I think that's what you show here. The one thing you always found was urine. And could it be that what you're calling coke could be solubilized off of those catalysts? That they are just merely very large aromatic compounds that,
Without a doubt.
okay.
Without a doubt, they could be multiple ring, large aromatic compounds. Unfortunately, you're really in a cracking regime. You are probably slightly oxidizing here. You're probably not in a releasing environment. And so the normal coking mechanism of aromatic compounds is they dehydrogenate and they go hydrogen deficient, and they become from an aromatic ring, they become a coke precursor, and then that polymerizes, and then it becomes a solid coke, and then it becomes a graphite material. And once you get to the stage where an aromatic ring, it becomes hydrogen deficient, I think you're dead. I don't think you have a chance then of getting that back off. Now, durine, I wouldn't call durine hydrogen deficient. It is a stoichiometric compound. But it wouldn't surprise me that you might be able to, at some shorter time than what they run, do a solvent wash of this catalyst to make it run longer. The problem is that'd probably just take just as long as a coke burn. And I really believe that most of the coke comes from multiple ring compounds, because these cracked light ends, they come right off. There's no problem there. The only thing that really can load up on the catalyst is aromatic. And so that's the quick route to coke, is aromatic compounds. Yes, sir.
You said earlier that the transalkylation reaction decreases before the alkylation reaction.
Yes.
Does that indicate there are two different types of acid sites on these catalysts?
It does to me.
Yeah.
What are the requirements?
It does to me, yes indeed. Yeah.
Because, pore blockage wouldn't be an issue here.
Well, I really believe that even though these things are the appropriate size, the pore openings are the appropriate size, I am a firm believer that reactions over zeolites occur at the pore mouths rather than inside the channels. And so, even at that, even if it coked, coking would probably, they can see coking sometimes with pressure buildup. So, it's external. It just builds up in the beds, external to the catalyst even. And so that's a good indication that, there's something, the way they mix the benzene ethylene and the way they inject it between beds at high temperatures are all conducive to ethylene oligomerization, thermal ethylene oligomerization. And I firmly believe that there's probably a lot of good work that could be done by an engineering company in quench nozzles, quench designs, things like that would alleviate a lot of these people's problems. Because, they've told me, they have coke 2 and 3 inches thick on these nozzles when they shut down and turn around, just from the ethylene being injected.
very interesting, informative talk tonight. I'd also like to thank UCI for allowing you to make the presentation, and FEMA too. And, I think if there are any other questions for Fred at this time, you can ask him after we adjourn.
Thank you for coming.
Yeah, I need to begin with an announcement. Dick asked me to announce that if anyone desires vegetarian lunches or dinners that have not already specified so in the registration, that they need to talk to Ken Campbell. Okay. And getting back to our program, our next contribution is from Union Carbide, Dave Minahan and Dick Nagaki. Dave got his BS from Manchester, PhD, then went on to Auburn University, and from there he postdoc at Ohio State. And they will be presenting a paper called Syngas to Fuel Alcohols MCBs.
Good morning, everybody.